In this video, I'm going to take you through mathematical induction. I have a series of examples here. Each example corresponds to a type of mathematical induction. Please, if this is the first time you are visiting this channel, kindly subscribe. Don't forget to like and share to your friends. So, I have the first example here, which is representing the series type. I have this, which is representing both inequality as well as the factorial problem. I have a series type also here, but in this example it has a higher power. Then finally I have divisibility here. Please watch this video to the end so you understand every part of the video. Now let's take our first example. So the first example is 1 squared plus 2 squared plus 3 squared plus n squared is equal to n multiplying n plus 1 multiplying 2n plus 1 all on 6. So let's see how we're going to solve this by mathematical induction. So by mathematical induction, the steps are the base step, the inductive hypothesis, then finally the inductive step. So let's see. For the problem we have here, let's test for the base step. The base step is a step we use to confirm if the statement is true for the least value of n. We are dealing with natural numbers, so the least value of n is what? 1. So for n is equal to 1. Now, when we talk about this problem here, this is series. So the sum of the first term, second term, third term, up to the nth term is given by this expression. If you say you are summing the first term, meaning you have to put 1 at the right side in order to get the answer. If you are summing the first 2 terms of this, then meaning you have to put 2 here for you to get the answer. So now let's test for n equals 1. For n is equal to 1, you realize that we are going to have the first term. So we are summing only the first term. N is the same as number of terms. Please take note of this. Number of terms. So when you say sum of the first term, it means that when n is 1, we are summing only the first term. So I'm going to have 1 squared on my left side should be equal to, at this point, wherever I see n, I put 1. So I have 1 multiplying 1 plus 1, multiplying 2 open bracket 1 plus 1, all out of 6. My left hand side will give me 1 because 1 squared is 1. This side I'm going to get 1 multiplying 2, that is 1 plus 1 is 2, multiplying 2 by 1 plus 1, that is 3, all on 6. I have 1 is equal to, this will give me 6, that is 1 by 2 by 3, all on 6, 6 on 6, which is 1. Therefore, 1 is equal to 1, so base case is true. You can go further to test for base case when n is equal to 2. And if n is equal to 2, you come here, you sum the first 2 terms of this sequence here. So I'm going to have 1 squared plus 2 squared, right? Should be equal to, here you put 2. So I'm going to have 2 plus 1, 2 multiplying 2 plus 1, all on 6. 1 squared plus 2 squared obviously will give me what? 5. Should be equal to, this will give me 3. 2 multiplying 3, 2 times 2 is 4 plus 1 is 5. All on 6, right? So you can clearly see that 2 by 3 will cancel this 6 and 5 will be equal to 5. Therefore, base case is true once again. Now let's move forward. So moving forward, we move to our inductive hypothesis. So our inductive hypothesis. So the inductive hypothesis is simply the point where we assume. So this is one of the important steps in finding or in using mathematical induction, because you are going to assume that our statement is true for n is equal to a chosen variable k. So you just write assuming the statement is true for n is equal to k, I'm going to have 1 squared plus 2 squared plus 3 squared. That is the problem. So plus k squared, remember, should be equal to, I'm going to have k multiplying k plus 1 multiplying 2k plus 1 all on 6. So I made a substitution from this side. So you can clearly see wherever I saw n, I put k there. So let's see, at this point, this whole statement here is true by our assumption. The next step is our inductive step. So the inductive step is the actual step when we are going to prove for our mathematical induction. So now what we write is proving for n is equal to k plus 1. Now we were able to assume that our statement here is true for n is equal to k. So for mathematical induction, we ensure that any statement you have brought up should be true for all natural numbers. And for it to be true, if you claim that the statement is true for k, then it should be also true for n is equal to k plus 1. So you are only to prove for n is equal to k plus 1. So at this point, wherever you see n, you put k plus 1 there. So you have 1 squared plus 2 squared plus 3 squared plus, then this part you put your k squared, then don't forget this is a kth term, so you add the k plus 1 term will also follow like this, should be equal to wherever you see k here, you put k plus 1. So we have k plus 1 out, multiplying k plus 1 plus 1, multiplying 2 open brackets, this place will be k plus 1, then plus 1, then everything over 6. So at this point, the goal is to ensure that our left hand side is equal to our right hand side. Once that is proved, it means our mathematical induction has been proved right. So how do we show that this side is exactly equal to this side? From our inductive hypothesis, you realize that 1 squared plus 2 squared plus 3 squared up to this side is giving us this whole expression. For that reason, we can replace this whole part up to this side with this expression, right? So let's make that substitution. So k multiplying k plus 1 multiplying 2k plus 1 all out of 6 is taking this portion, because our inductive hypothesis is saying that this expression here is true, meaning if I make this substitution, then it means it's also true. That is for only this section. So I'll continue on plus k plus 1 all squared. This should be equal to this side k plus 1 in 1 bracket. This will give me k plus 2. Take note. Then this side is 2k plus 2 plus 1. So we are going to get 2k plus 3, right? So 2k plus 3 all out of 6. So let's prove that our left hand side is still equal to our right hand side. So let's see. At this point, we know from algebraic expression you need to multiply this 6 by this. So you get k multiplying k plus 1, multiplying 2k plus 1, multiplying 6k plus 1 all squared, all out of what? 6, right? This should be equal to what we have here, k plus 1 in one bracket, k plus 2 in another bracket, 2k plus 3 in the third bracket, all over 6. At this point, we want to make this side equal to this. Our denominators are equal, so meaning we have to focus on the numerator. At this section, we can factorize k plus 1 out from here. So k plus 1 will come out, and I'll have, when k plus 1 is out here, to be left with this and this. So I'll have k multiplying 2k plus 1, right? Then this side will give me plus 6 multiplying k plus 1 should be equal to k plus 1, k plus 2, sorry. So k plus 2, then this side is 2k plus 3, all out of 6, all out of what? 6 here. We move on with our simplification, and at this point we can simplify what is in here. So k plus 1 out. What I have here will be 2k squared. So k times 2k is 2k squared plus k, plus this side is 6k plus 6, all out of 6 should be equal to k plus 1, k plus 2, 2k plus 3, all out of 6, right? So at this point, I will get here to be k plus 1 out, here to be 2k squared plus 7k plus 6, all out of 6. Now, since I have k plus 1, I have k plus 1 here, then let me also multiply what I have here in order to get something like this. So k multiplying 2k will give us 2k squared, k multiplying 3 will give us 3k, 2 multiplying 2k will give us 4k, and 2 multiplying 3 will give us 6. Everything out of 6. So we get k plus 1 in one bracket, multiplying 2k squared plus 7k plus 6, all on 6 should be equal to k plus 1, 2k squared, then this is going to 3k plus 4k is also 7k plus 6, all out of 6. Now we can clearly see that our left hand side is equal to our right hand side. Therefore, our statement is true for all natural numbers. So meaning that we are successful and we are proving that our statement is true for all natural numbers, and that is only for the first problem. So let's quickly move to the second problem, and the second problem is a problem involving inequality as well as factorial. So the second problem is 2 to the power n is less than n factorial for n greater than or equal to 4, right? So having this problem, and as we did in the earlier problem, our base case is always tested first. So our base case, and you know our base case, we are going to take the least value of n. This problem we have here says it is only true provided n is greater than or equal to 4. Take note. Hence, the least value we can get is 4. For that reason, n is equal to 4. I'll be getting 2 to the power 4 less than 4 factorial. And this is going to give me 16 is less than 24. And this is true. Therefore, our base case is true, right? This case has been tested, and now, as usual, our inductive hypothesis. So let me make it IH, right? To make things short, you assume that the statement is true for n is equal to k, right? So once you have that, you get 2 to the power k is less than k factorial for k is greater than or equal to 4. And this, as you have here, is true. Then we quickly move to the inductive step, where we are proving for n is equal to k plus 1. And at this point, wherever I see k, I put k plus 1. So 2 to the power k plus 1 is less than k plus 1 bracket factorial. So this is fully averaged. And you know, mathematical induction, our goal is to prove that our left hand side here is what? Exactly satisfying what we have here. And in this problem, our left hand side will be less than this. So how do we prove that? We can only do that by making use of our axiom or our assumption here. So this is what we are going to do. The main importance of our assumption is for us to use that to solve this. So always, the first thing to do is to draw a relationship between your assumption and your inductive step. And for that reason, you make one of the sides equal. So let's see, this one is also written as 2 multiplying 2 to the power k from indices k plus 1 all factorial, right? So once we have this expression here, the next thing we are going to do is, you can see that our assumption is 2 to the power k, right? So we need to make our assumption look exactly like this, so that we can easily prove for what we have. So now let's see. Our assumption is saying that 2 to the power k is less than k factorial, right? So at this point, this is what we do. We will multiply 2 by our assumption, so 2 multiplying 2 to the power k less than 2 multiplying k factorial. Once you multiply, you can clearly see that this side, let me make it 1, and this side 2, they have the same left hand side, meaning that if you are able to compare these two, then you will clearly see that this side is less than this, right? That's our goal. We have to show that 2 multiplying 2 to the power k is just less than k plus 1 factorial. So how do we do that? We simply do that by using our hypothesis. And our hypothesis, we have simplified it, or we have modified it to look like this, and we have our left hand side in common. So now let's focus on the right hand side and see. So from this here, you know that when you have a factorial, that is this side. You know, when you have a factorial, it is the same as what? 2. Then the k factorial here will be k multiplying k minus 1, right? Then you introduce your factorial, because you go k minus 2, k minus 3, k minus 4, but let's stop here and see. So meaning 2 to the power k is less than this, right? So let's stop here. Now from this side, that is from 1, you realize that we want to consider this. Let's expand this further so that we can draw analogy here. Because this k plus 1 factorial, we need to expand. So from 1, we get 2 multiplying 2 to the power k, right? Less than what? If you have k plus 1 all factorial, then what are you going to get? You get the number. Remember, n factorial is n itself multiplying n minus 1 multiplying n minus 2. So in that order, factorial, meaning that I'll start from what? K plus 1 multiplying this minus 1, then that will give us what? K, right? Then multiplying k minus 1 factorial, and I'll stop here because I only want this to look like what? This when we compare. Once I have expanded my equation 1, so the inductive step is still this, so that is our equation 3. We only expanded this side. Then for our axiom, we make sure that we modified it to look like this, and at this point we expanded the p factorial to get this. So now let's see. This is our axiom. Everything here is true. That is the most important thing. But in this place, what is the hypothesis? We have to compare these two and draw our final conclusion. So you can see that I have k minus 1 factorial, I have k minus 1 factorial also here. I have k, but I still have k plus 1. Therefore, you can see that 2 multiplying k minus 1 factorial is less than what? K plus 1 multiplying k minus 1 factorial. Right? This is less than this. And you know 2 multiplying 2 to the power k is also less than this. So if this, that is a, is less than b is less than c. Obviously a is less than 1 c. So if 2 multiplying 2 to the power k is less than 2, multiplying this, then this whole thing is also less than this. Then obviously 2 multiplying 2 to the power k is less than k plus 1 k minus 1 factorial, and that is exactly from our hypothesis. So meaning our hypothesis is true because we have used the assumption to prove that indeed 2 multiplying 2 to the power k is less than this. We have k minus 1 here, we have k minus 1 here, we have k, but we still have extra 10, making this bigger than this. And if this is less than this, obviously this will be bigger than this, right? So that makes this true, and therefore our statement is true. So therefore our statement is true. So this is how we go by the inequality and the factorial problem. Now let's see our third example. And our third example is also a series 1 cube plus 2 cube plus 3 cube plus n cube is equal to n squared multiplying n plus 1 all squared all over 4, right? So in this question, what are you going to do? As usual, our base case. So when n is equal to 1, you have the sum of the first term. Don't forget, in the series, we tackle the sum of the first, sum of the second, sum of the third, not this side. So we are going to have 1 cube, that is this one, should be equal to our this side. So I'll put 1 here. So I'll get 1 squared here, 1 plus 1 all squared, everything out of 4. So I'm going to get this side will be 1, should give me this side is 1 plus 1 here, all squared 2 will be what? So let me make it 1 multiplying 2 all squared all over 4. And once you have this, we are going to get 1 is equal to 4 over 4, and I'll have 1 is equal to 1. So therefore, this case is true. So once the base case is true, we move to the hypothesis. So you know hypothesis, we assume that our n is equal to k is true, right? So let's quickly do this. So once our n is equal to k is true, then easily we can say that our 1 cube plus 2 cube plus 3 cube plus k cube will be equal to k squared multiplying k plus 1 all squared over 4, right? That is from what we have here. So we just substituted this side, and once we have this, we can come to the inductive step and make it inductive step. So proving for n is equal to k plus 1, Alright, proving for n equals k plus 1, our series becomes 1 cube plus 2 cube plus 3 cube plus k cube, right? It's a series, so this one will maintain. Then we add the k plus 1 all cube should be equal to k squared multiplying k plus 1 all squared all out of 4. Alright, once you have this, then we are good to go to prove that our left hand side here is equal to right hand side. But we can only do that from our assumption. From our assumption, we know that all this side is giving us this expression. So I'll replace this whole side with the same expression, k squared multiplying k plus 1 all squared over 4. Then you know this part that we replaced, so this one will continue, plus k plus 1 all cube is equal to k squared multiplying k plus 1 all squared all over 4. So let's see. So at this point, you realize that we have to just show that this side is equal to this side. And to show that it's simple. From algebraic expression, you multiply this by this, you divide. So I'm going to get k squared multiplying k plus 1 all squared plus 4 multiplying k plus 1 all cubed. That is this side cross multiplying for this over 1 all over 4, right? Should be k squared k plus 1 all squared all on 4. At this point, you factorize us k plus 1 out, or let's factorize k plus 1 squared out. So you can get k plus 1 all squared because that's the bigger one here. Into bracket, it will go here k squared plus what? 4. Then here it will cancel 2, so it will be left with 1. K plus 1, right? Everything here over 4 should be equal to k squared multiplying k plus 1 all squared all over 4. So let's see. When I was proving for k plus 1, for n equals k plus 1, this side I didn't replace it with k plus 1. So making that correction, I'll clean. So I'm going to clean this side and I'll replace it with k plus 1 because I need to replace it with k plus 1 from this side. So I have to take that off. So I'll have k plus 1 so I'm going to have here k plus 1 all squared multiplying k plus 1 plus 1 all squared all over 4. Likewise this place. So I'm to make the rectification here. So this place will also be the same. I'll clean this side and I'll clean this place. So I move on to finding this side. So here will be k plus 1 all squared multiplying k. So here will be k plus 2, right? All squared and all out of what? 4, right? So here comes back k plus 1 all squared, k plus 2 all squared, all out of 4. So here becomes k plus 1 all squared, k plus 2 all squared, all on 4. So now let's see. So this side I'm going to get k plus 1 all squared. Then this side is giving me k squared plus 4k plus 4 all out of 4 is giving me k plus 1 all squared, k plus 2 all squared out of what? 4, right? So we have to show that this and this are equal, and that is simple multiplication. So k plus 1 all squared for this side q squared plus 4q plus 4 for this side, and this will be equal to k plus 1 all squared here. Multiplying this is q squared plus, that is 4q plus 4 all on 4. And you can clearly show that our left hand side is equal to right hand side, and therefore our statement is true for n, which is all natural numbers. Now let's go to our final example for this, and our final example, that is number 4, is same. So this is the final example in this round. We have to show that n cubed plus 2n is divisible by 3. In divisibility problems, it follows the same order. We test our base case, and you know, for the base case, you make sure that we test for n is equal to 1, where n should be the least number. In this case, n is equal to 1 is permitted. So I have 1 cubed plus 2 multiplying 1. That is going to give me 1 plus 2, which is 3. And it is divisible by 3. Therefore, base case is true. At this point, the next thing we are going to do is our hypothesis. For the hypothesis, you assume n is equal to k is true, and we are going to get k cubed plus 2 multiplying k is divisible by 3. And to show that it is divisible by 3, let's make it equal to 3 multiplying a variable. So meaning this is true. Now let's continue with our inductive step. Our inductive step, we are going to show that n is equal to k plus 1 is true. So we are going to replace k with k plus 1 plus 2 multiplying k plus 1, right? So this is the actual problem. This was just it's just showing that this is divisible by 2. So now let's expand what we have here and see. You get k cubed plus 3k squared plus 3k plus 1 plus 2k plus 2. You get k cubed plus 3k squared, then 3k here, right? Then plus 1 plus 2 is 3, then plus 2k. But remember that from our inductive hypothesis, k cubed plus 2k is equal to 3n. So we simply replace k cubed plus 2k plus 3k squared plus 3k plus 3. I replace this with 3n, so plus 3k squared plus 3k plus 3. At this point, I can factorize 3 out and I'll get n plus k squared plus k plus 1. Once I've been able to factorize 3 out, we can clearly see that this is divisible by 3. Hence, our inductive approach is valid. And therefore, for n being a natural number, n cubed plus 2n is always divisible by 3, and we have proved that by induction. So this is the end of this series. Thanks for joining, and I hope you really enjoyed the class. Please like, subscribe, and share.